Hey, AP Stats, this is just a quick reminder video coming back after spring break. So I want you to look at the whole set of chapters that we're about to kick off with remote learning. All kind of starts with recalling a piece of lessons that we did in chapter 18, where we started by simulating 600 dice rolls. And that means we kind of thought that we'd have something looking like a uniform distribution where if we're rolling a dice 600 times, we should think that we're getting right about 100 of each of the six. It's a uniform distribution because they're all the same. So just make note that it's definitely not a normal curve. Okay, so the difference is we're starting with something that is definitely not normal, but we are moving to taking distributions of sample means. Sample means meaning taking one of those 600 dice rolls, adding it to another of the 600 dice rolls, adding it to another random piece of those 600 dice rolls, and then dividing it by how many we sampled. So this is a distribution of sample means, and two different ideas of when we have a relatively small sample size, n equals 5, versus n equals 100. This distribution of sample means come to looking something like these normal curves that I drew. Technically, we're not going to call them normal curves in the near future, but right now they're going to look like it. The actual averages should come out to 3.5. Oh, and prior to this video, I took the stats from that for, if we assume that this 600 is a population, instead of a sample, we'd have mu mean 3.5, and the standard deviation was 1.69. I ran those stats in advance. They are actually right here. Anyways, we're going to use these because this distribution of sample means is centered at that 3.5, but the distribution of these sample means does not have the same standard deviation and is dependent on our sample sizes. We take the standard deviation of the population, 1.69, divided by the square root of n. And I think this one came to 0.76. So that means when we build up 3.5 plus 0.76 and plus 0.76 again, I'm going to two standard deviations, was 5.02. If we go down 0.76 and down 0.76 again, it'd be 198. Meaning if I'm going to take 5 rolls and average them out, most of them are going to really be between that 1.98 and 5.02. But when we take a relatively large sample size, 100, that means we're taking population of the sample size, standard deviation of the population, 1.69, divided by square root of the sample size 100, we're going to get 1.69, or I'm going to say about 0.17. It's worth comparing really quick the sizes of our standard deviations of sample means, meaning the larger sample size is much smaller than when n was 5. So if I go up 2 standard deviations, that'd be only 3.84. And if I go down 2 standard deviations, it's 316. Compare these two really quick. Boom, there's a whole bunch more on the screen now. So we started with a uniform distribution here. We took sample means, and when we took these sample means, it made a mostly symmetric, mostly normal distribution with much less spread than our population. When we increase the sample size, we have much less spread, which implies larger samples are more predictable.